Good afternoon, ladies and gentlemen. Welcome. This is again 4ST441, Statistical Methods and Capital Markets, and our fifth seminar. So we can start. We will talk today about Aroma and Aroma Models. At previous seminar we tested autocorrelation in time series. Yes, we talked about the correlation structure inside the time series, because the real time series which are generated outside, yes, outside, so the real time series and the real economics contain some correlation structure, some generation process. Yes, we have seen that autocorrelation is rather weak in the time series of stock log returns, but present in time series of square log returns. Aroma models are used to model time series which exhibit autocorrelation. It means linear dependencies. Maybe not only linear dependencies, there is sometimes more complicated structure, more complicated dependence. Yes, linear is the base, yes, but very often it is more complicated. The correlation not only between neighborhood values. Yes, do you remember, for example, Darwin and Watson statistic, Darwin-Watson test of correlation? Yes, the test of correlation of neighborhood values. So this is the linear, yes, dependence, but sometimes it's a little bit more complicated, but we will talk about this later. The linear dependence imposed by an Aroma model for log returns or other time series, yes, will often be rather weak or known. Yes. However, in order to understand models of volatility, GAR and R, yes, which will be introduced later, it is useful to understand Aroma auto-regressive moving averages, yes, Aroma models at first. Okay, so because we need to understand these models, it's necessary to know what is it, stochastic process. Yes, in the basic course of statistics, we are very often talking about deterministic process only. Yes, deterministic trend and deterministic seasonality. Sometimes we are talking about the macroeconomic cycles. Yes? Macroeconomic cycles, the changing of period of growth with the period of decreasing. Yes, this happens sometimes. Yes, every 6 years, 8 years, 10 years, etc. Yes? The macroeconomic cycles, the changing of growth with decreasing. But the trend and seasonality can be either deterministic, when you know, when you can observe the deterministic trend, the deterministic development, yes, of the time series, and deterministic changing, deterministic fluctuation around the trend. Yes, for example, because of changing periods, because of changing the working days and weekends, because of changing Mondays and Fridays, etc. So we can observe the deterministic behavior. Yes. But in the real time series and complicated time series in economy, we can also observe the stochastic process, which is invisible by eyes. Yes? If you check the development of the time series, just the simple development by line and symbol chart, you are not able to see the stochastic process. Stochastic process is hidden inside this development, and can be evaluated by some special tests, by special methods, etc. And about this we will talk now. Yes? Stochastic process is a sequence of random variables. This is very important, random variables. You are not able to see by your eyes the random variable, because it's random, yes? Random variables, x1, x2, x3, etc. ordered in time. We will use the following notation, x1, x2, x3 in these parentheses, yes? Or briefly, x in time t in these parentheses, where t represents the time. Realization of a stochastic process, it means the situation where the random variables may be better the values of random variables, yes? Because we have a random variable and values, a series. Stochastic process is a series, yes, of values of a random variable. Yes? The situation where the random variables, the values of this random variable of the stochastic process take specific values is called a time series. We will continue with stationary stochastic process. Maybe you already seen, for example, white noise or other process, yes, which fluctuates around some conditional mean, some conditional average value. Yes. In general, the properties of the random variables can change over time. Yes. One assumption can be stationarity. We already talked about stationarity because you remember augmented Dickey-Fuller tests. Yes, we talked about the test with no intercept and no trend. Yes, the model with intercept and the model with intercept and deterministic trend. Yes. So one assumption can be stationarity. We know what is stationarity and non-stationarity. We tested stationarity as of the time series in one of the previous seminars. You remember this. Stochastic process is stationary if expected value, yes, of xt is equal to mu. So expected value, the mean, the conditional mean, yes, is equal. It can be 0, it can be 1000, yes, it can be 1 million or minus 500, yes, but mu, still the same mu, yes. Expected value is a constant. Variance of xt is sigma squared. Sigma squared means that the variance is finite and constant in time, yes? What it means that the variance is finite? It means that it's not possible to have the development of time series where fluctuations increases, for example, to infinity, because if you calculate the variance, there will be infinite variance and it's not a constant. So variance can be equal to 1 million squared units, 1 billion squared units, but it must be finite variance, yes, and also constant at the particular level of significance, constant in time, yes. So of course there can be small differences, but it must be constant in time at the particular level of significance. And the covariance between the value, this is the value of random variable xt, and random variable in time xt minus 1, so previous value, must be equal to gamma tau. This means, yes, gamma tau, that the covariance is again constant, yes? Maybe I will recapitulate this mean and variance of random variables and the covariances between random variables separated by tau do not depend on time t. So this is the most important, and this is the summarization of these three issues. Okay, so we can continue about stationary stochastic process. A stationary time series is a time series which is a realization of a stationary process. Yes, such a time series does not exhibit trends or seasonality. It always reverts to its mean mu. A non-stationary time series is a time series which is a realization of a non-stationary process. Such a time series can exhibit trending behavior or seasonality. Maybe I can illustrate this for you. You've already seen non-stationary time series. Non-stationary time series has its own development, has its own trend. Yes? The trend is either decreasing or increasing, or this time series has macroeconomic cycles. Yes? The long-term macroeconomic cycles contain seasonality, the changing fluctuation, yes? Changing fluctuations around the trend, which depends on changing of, for example, seasons, yes? Weeks, quarters, months, etc. Yeah? The changing of seasons. A stationary time series doesn't have this. Yes? A stationary time series only fluctuate around some conditional mean, around some conditional mean value. So we can move here, and we'll speak about the white noise, or we can say white noise process. What is it, white noise? White noise is an example of a stationary stochastic process and has the following properties. Expected value of this white noise process is equal to 0. So you can imagine that there is a line, x line, as x-axis in the chart, and the values of this process fluctuates up and down around this 0 value. If you calculate the mean, the mu, the expected value of this process, it will be very close to 0, 0.00001 or minus 0.0001, very close to 0, yes? The variance, the measure of variability, variance of this white noise process, xt, is equal to sigma squared, and this is the same characteristic and the same meaning which I already said before. So the variance must be constant in time and finite. Yes? The variance can be equal to 1 billion, 5 billions, or 10, 0.1, etc. Yes? But it must be constant and finite, constant in time and finite. Yes? And rho tau is equal to 0, for tau is equal to 1, 2, 3, etc. And this is no correlation. The values of the white noise process must be absolutely non-correlated. There is absolutely no correlation, absolutely no dependence between any value of this white noise process. It is absolutely not possible to predict the white noise process because there is absolutely no system inside this. Yes? So white noise process is an example of a stationary stochastic process. We can continue. An independent and identically distributed white noise is a special case of white noise where, over and above the properties of white noise, the random variables are independent and identically distributed. Yeah? So this is the special situation, but standard, yes, in standard situation, in standard examples, and in many applications is enough. Yes, is enough for us, where we evaluate something and we require just white noise process. Yes, this independent and identically distributed white noise is a special case. Yeah? So it's good to know that this exists. Yes, a Gaussian white noise is a special case of a white noise where the distribution of each random variable is normal. About this Gaussian white noise we will speak more, because we will create a lot of models, yes, in our seminar and in other seminars at the Prague University of Economics and Business, where we analyze time series. Is necessary when you estimate the fit the data by appropriate model, as regression model or regression time series model, etc. Evaluate the residual diagnostic, evaluate the residuals, yes, in this model, and you will see that we will talk about this Gaussian white noise in a situation where we will speak about the residual control. Yes, so that is very important. This word normal, you already know what is it, normal distribution. You would seen before the histogram in EViews, yes, and you know that there exists a Jark-Vera test, Jark-Vera statistic, where our zero hypothesis was the distribution is normal. There is normal distribution of the data set, yes. Alternative hypothesis, the distribution is not normal, yes. So the fourth characteristic, expected value equal to 0. The variance is constant and finite. Absolutely no correlation and normal distribution. So the fourth important characteristic for the white noise process, and we have Gaussian white noise. We can move to autocorrelation functions of stationary stochastic process. We already see before the autocorrelation function, yes, AFC. We know that autocorrelation function is a series of correlation coefficients or autocorrelation coefficients. So the values from range -1 + 1, yes, which can be illustrated in chart, yes, either positive columns or negative columns, yes. So the autocorrelation function of a stationary process is defined as, there we have a formula, rho in tau, yes, is calculated like gamma tau divided by sigma square, the variance, for tau equal from -1 to 1, etc. We can write rho 0 is equal to 1 and rho in minus tau is equal to tau. Therefore, it is sufficient to study the autocorrelation only for positive flux. Yes, in EViews you could see before that there was a question, yes, about the number of lux where we checked the structure of the correlation. Yes, number of locks, 12, 16, 36, etc. Yes, and we could see the development of these correlation coefficients represented in the chart. Yes. The autocorrelation function of a stationary stochastic process does not change over time and can be estimated using the sample autocorrelation function of the time series defined in the previous weeks. Yes, the chart. Yes, the chart of the autocorrelation function is estimation of autocorrelation function, because our time series, which we analyze, is a sample, a statistical sample of 280 observations, 365 observations, etc. It's, for example, 1 year, yes, or I don't know how many months, etc. But it's a sample, and because it's a sample, we have here a sample autocorrelation function. Okay, we can move to exercise 18. We will generate a realization of a Gaussian white noise with unit variance. We'll calculate a sample and true autocorrelation function and discuss the result. Sample and true in our situation will be the same, because we will generate a Gaussian white noise, for example, with 500 observations. Yes, it's not possible for us to generate a series of billion values, 10 billion values, etc. Yes, or infinity values. So we must set, for example, I think that 500 will be enough. Yes, 30 is the minimum, but our statistics works better if we have large samples. Yes? So I recommend to you generate a realization of 500 independent values, yes, of Gaussian white noise, and we will use Microsoft Excel calculator. We will transform, we will copy these generated values to views, and after we will evaluate this process in EViews software. Okay, so I have here opened Microsoft Excel sheet, and we will start with generating of the Gaussian white noise process. So we need a generator of random numbers. So we need to install a special add-in to Microsoft Excel. So if you have open this blank workbook, you can click on File button. Yes, on the top left corner of the window you can see File button, and there on the bottom you can see Options. So please click on Options, and you will see the window, yes, where in the left column you can find add-ins. So we will click on add-ins, and there on the bottom of this window we have Manage Excel add-ins. So there is Excel add-ins, there is Go button with 3 dots. So please click on this Go button with 3 dots, and in this small window we will select Analysis Toolpack. So please select Analysis Toolpack and click on OK. Okay, so on the data leaf, yes, data leaf, in the right top corner there was nothing, yes, before, but now we installed here a special analysis toolpack, data analysis. So please click on this data analysis, and within few seconds you will see this small window with a lot of statistical tools. and we will find here random number generator. Yes, random number generator. And we will click on OK. It's necessary to generate a variable. One variable with a lot of values from this random variable. So we will generate one variable. Yeah? So number of variables will be equal to 1. Number of random numbers must be higher than 30, but enough for our purposes. I recommend to you set here, for example, value 500. Yeah, so we will write here 500. The distribution, we select normal. So please select normal distribution, and there we have parameters. If we set 0 mean and standard deviation equal to 1, it means that the variance sigma squared will be also equal to 1, because 1 squared is equal to 1. So this will be standardized normal distribution. Standard normal distribution. Output will be generated, for example, on new worksheet. Yeah, so we can click on OK button, and you will see here a series of 500 values which should be independent. Yes, so we can zoom a little bit, zoom this document, okay, and we can scroll up to the first cell. Okay, so this series of 500 values will be placed to EView software. It's necessary to change the commas to dots. Yeah, so please select this series of 500 values. Yes, for example, Control Shift and arrow down, and we will use a shortcut Control H for find and replace. Control and H button. Yes, so we must find commas and we must replace with dots, because EView is English-speaking software and requires dots instead of commas. Yes, and I have here set commas, and many of you probably have programmed set commas in Microsoft Excel. So if we replace all, you will see that we made 500 replacements. So we will click on OK, and here we have a series of 500 values with dots. So now we can open Microsoft EView. We can open EViews. We can open EViews, and in EView software we will click on File button, and we will set New, because we need to create new workbook. So we will find here new work file. Okay, we must set work file structure type. So it will be dated, regular frequency. We will set frequency, not annual, but integer date. Integer date, because we have 500 observations. So start date will be equal to 1, and end date will be 500. Okay, that's all. So we can click on OK, and you will see here a work file, yes, with 500 observations. Now we must create a file for the white noise process. So in the command block, we must write the command. So we can zoom the font, and we will write series, and we will name the new file, for example, AT, like white noise process, int equal to 0, equal sign 0, and enter. And we will see here this file, so we can double click on this file, and we must click on edit plus minus for unlock this sheet. And from Excel we can copy and paste these values. So from the top, yes, to the end, these 500 observations, copy Ctrl C, yes, and to views here from the beginning, Ctrl V, paste. And you can see everything is alright. Yes, we have here 500 values. Now, this is a white noise process, or this should be a white noise process. So please, click on View button and click on Graph, and we will check the development in line and symbol chart of this process. Yeah, so please click on OK, and there you can see the fluctuations. You can see the fluctuations around 0 because we set the generator on standardized normal distribution with 0 mean and sigma square equal to 1. So this should be standardized normal distribution. We can verify if this is normal distribution. You can click on View button and you can find descriptive statistics and tests and histogram and stats. Oh, there is normal distribution, a histogram of normal distribution. Jarve statistic is very, very small. P-value is almost 100% because we set to the generator that this must be a process from normal distribution, values from normal distribution, yes. You can see that mean is minus 0.02, very, very small, yes, very close to 0. This deviation is random, yes, because it was a random generator of random numbers, yes. It must not be 0 exactly, yes. Every time you have small deviations, yes, but this deviation is not significant. And our duty was to calculate autocorrelation and partial autocorrelation function. So in Excel, in eViews, please click on View button, and there is correlogram. So please click on correlogram, and we will select correlogram of level, correlogram of values, which you could see in the development of this time series. So please click on OK, and here you can see autocorrelation function, or the values of autocorrelation function, and the partial autocorrelation function. And if you remember the Young-Box-Q statistics, yes, and Young-Box test of correlation, zero hypothesis is there is no correlation, there is no correlation structure, there is no dependence, the data is independently distributed. You can see that all p-values, yes, some exceptions, yes, are here, but the main is at the top, yes, so there is no correlation between values, no correlation between values without the influence of other values, etc. You can see that practically without some small exceptions. No, there is no exception because you can see that there is p-value 0.195, yes. So this is white noise process. A problem is if you have here on the first position, mainly on the first position, p-value below 5% significance level. It means that there is a correlation between xt and x in time t minus 1, so the correlation between neighborhood values, and this is a serious problem. So if you have here p-value below 5%, you must generate new process of white noise process in Excel, yes, and put it to use and verify if this is really white noise process. So this is our Gaussian white noise process with zero mean, constant and finite variance, no correlation and normal distribution. Okay, so let's start with Aroma Models in detail. It's important that it's a shortcut of autoregression moving average models designed by George Box and Gwilym Jenkins. They consist, these models, yes, they consist of AR, autoregressive, and MA moving averages processes. So two different processes. Sometimes there is integration of certain order, E integration. So we have Aroma models. Yes, the integration is either first order or the second order, and the integration is connected with differences, the differentiation of the time series. Yes, maybe you already hear about these differences and this integration. If the time series is stationary after first differences, this time series is called integrated of the first order, and if the time series is still not stationary after first differences and is stationary after second differences, this time series is called integrated of the second order. Yes, so the order of integration, but we will speak about this order of integration also later. Yes, in particular cases where seasonality is present, the models are extended to SARIMA. Yes, mainly SARIMA models are created, established on quarterly and monthly time series, but weekly published data, for example, also contain seasonality, some kind of seasonality, but we will speak about this also later. So it's necessary to show you how it looks like the formula of autoregressive process or autoregressive model. AR1, this number, yes, is denoted like small p, yes, and you can see p is equal to 1. AR, autoregressive process, autoregressive model of the first order, is the model where p is equal to 1, and we can write that value x in time t is equal to, this is a constant, yes, phi 0, which can be placed to the model if is significant or is omitted, yes, if this constant is not significant. So the most important for us is that x in time t is equal to phi 1 x in time t minus 1 plus at. So this is autoregressive model of the first order, and now it's necessary to say what is written here. The constant is not interesting for us. The most interesting for us is the parameter phi 1, which is the measure of dependence on the previous value in the particular time series. Yes, I in time t depends on me in time t minus 1, yes, in such way, phi 1, yes. So this phi 1 is a measure of dependence on my previous value, yes, plus AT plus some value from the white noise process, yes. So that is written where phi0 is a constant which can or cannot be placed in the model. Phi1 is a parameter and AT is white noise with mean mu a equal to 0 and variance sigma a squared. Yeah? So with mu equal to 0, 0 mean and finite and constant variance in time. Yes? So this is the basic structure of the model and the basic principle of autoregressive model. Autoregressive, yes? It means that I in time t depend on me, yes, in time t minus 1 in some way, yes? And this is represented by this parameter phi1. The model is stationary if phi1 is smaller than 1, otherwise it is non-stationary, yes? Maybe later we will speak about the special process which is called random walk, yes? So you will see, yes, anything else about this parameter phi1, yes? But now it's only autoregressive model, autoregressive process. So the model is stationary if phi1 is smaller than 1, otherwise it is non-stationary. First we will talk about stationary AR1 models, then about general autoregressive models, yes, autoregressive of the order P. Okay. Something about partial autocorrelation function. You remember the charts in e-views, yes? The charts of the correlation structure, where you could see autocorrelation and the partial autocorrelation function, yes? Partial autocorrelation function is the function on the right side, yes, the right one. The left one is autocorrelation function, the right one is partial autocorrelation. It's a very important tool for determining the order P of an autoregressive model. Let us assume a stationary process xt, log k, partial autocorrelation function of this process is denoted as phi kk. Log k, partial autocorrelation function of this process, is the correlation between xt and x in time t minus k, yes, where effect of the intervening variables x in time t minus 1, t minus 2, t minus 3, etc. until t minus k plus 1 has been removed. So, without influence, yes, the partial autocorrelation function informs you about the correlation between any values in the time series without, yes, intervening variables lying between them, yeah? So this is very important. So there is exercise 19. We will generate a realization of an autoregressive process of the first order, yes. AT is a Gaussian white noise with unit variance. Yeah? So we have a white noise process, and you already know that white noise process is a process of values. Yes? It's a series of values with the same probability distribution, normal distribution or standardized normal distribution. yes, with zero mean, variance sigma squared, yes, with non-correlated values, with absolutely non-correlation of values. And now we will start with correlation. We will correlate this non-correlated process. And there we have four formulas where we have written x in time t will be equal to 0.3 times x in time t minus 1 plus a value of white noise. X in time t is equal to 0.5 times x in time t minus 1 plus at. X in time t will be equal to 0.7 times x in time t minus 1 plus a value from the white noise process, etc., etc. So you can see that there is autoregressive process of the first order without constant with increasing power, increasing value of the parameter phi. So we will increase the measure of dependence on my previous value, yes? Me in time t depends, yes, on me in time t minus 1, yes, in such way. And we will check the strength of this dependence, and we will try to explain how the time series were generated, yes? We will calculate the sample and true autocorrelation function, the sample and true partial autocorrelation function, and we will discuss results, yes? And we will try to forecast this generated time series. Okay, so we are back in Microsoft Excel, and we would like to generate autoregressive process of the first order with different value of parameter phi. So with different value of the measure of dependence of the previous values of variable x. So please, it will be good to generate new white noise process, uncorrelated series of values of random variable with the same probability distribution. Yes, so we have here Microsoft Excel, and we will use the data leaf. You remember that we have here data analysis. In data analysis, you can see that there is already selected random number generation. So please click on OK button, and there we have selected number of variables 1, 500 numbers of this random variable, normal distribution with zero mean and sigma squared variance, and also standard deviation in this situation equal to 1. So please click on OK, and you will see in your sheet a series of 500 values of this white noise process. Yes, we already showed a proof, yes, that this is a Gaussian white noise process, yes? A series of uncorrelated values. Okay, so now we will correlate. We will correlate this process because this is a series of non-correlated values. We will create in column B, C, D, and E 4 correlated processes. So if you remember the formulas which were written in my presentation, we will start here in this first cell. Because we don't have a previous value, there is only equal sign, and this A1, yes, this noise. And now I have my own previous value, yes. So if you remember, we used parameter phi equal to 0.3, like the first one, yes? So please, right here, equal sign, this parameter phi 0.3, yes, times my previous value, yes, this one, plus a noise on the row where I am. Yes, so this value of the white noise. Okay, and this can be copied. Yeah, so you can double click on this point. Yes, and you can copy this formula to the end. And if you check, for example, this formula here, you can see there is 0.3 times my previous value plus the noise on the row where I'm placed. Yes, and in the same way we will solve all other processes. So in the C column, yes, I don't have my previous value, yes, because I am in the first row. So there is only the value of the noise. Yes, so equal sign noise from the first sample. But now I already have my previous value, so we will increase the power of parameter phi on 0.5 times my previous value plus the noise, the value of the noise on the row where I'm placed. Yes, okay. We can copy this to the end and we can continue, yes, in the same way here. So again, there's equal sign, noise on the row where I'm placed, yes, only. And here, equal sign, increased power of parameter phi 0.7, for example, yes, times my previous value. My previous value in the column plus the value of noise on the row where I am placed. Yes, okay. And this can be copied to the end. And finally, in this E column, again, equal sign, the noise on the row where I'm placed, because I already don't have my previous value, xt minus 1, and there we will use, for example, 0.9. 0.9 times my previous value plus the value of noise on the row where I'm placed. Okay, so this will be copied to the end. And now, very important, we must select 2000 values. Yeah? So from the end, you can see 4 cells. We can use, for example, shortcut Control, Shift and arrow down. And now we must delete formulas from this matrix. Yeah? So we will use copy, Control C, and on the home leaf we have paste, and we will paste values only, 1, 2, 3, paste values. Yes, so copy and paste values, and now we don't have formulas in this matrix of 2000 values. And now we will find and replace commas on dots. So again, yes, please select these 2000 values. So again, 4 cells on the top, Control, Shift and page down, and we will use Control H, the shortcut Control H, find and replace. We must find commas and replace with dots. Yes, and we will click on replace all, and you will see all done. We made 2000 replacement because we have 4 times 500 values, which will be placed to eViews software. Okay, so please leave this and open eViews, and there is our work file with our white noise process, yes, with our white noise process AD. So we must create here, 4 new files. So we'll start with write series, and we will name this, for example, AR, like Autoregressive. Instead of space, we will use this 03 equal to 0. Yes, equal to 0. Okay. So this will be enter, this will be the first file, and we will continue in the same way. Series AR space 05 equal to 0, enter. Okay, and we will continue series AR space 07, yes, equal to 0. And finally, we write here series AR 09 equal to 0, enter. So now we have here 4 files, yes. We will open these files together, so please close this and select AR3, AR5, AR7, AR9 with control, yes. Like in Windows when you are selecting more photos, for example, more files, etc. Yes, you will use right button. You will open as group, yes, and you can see that we have here 4 columns. We must click on edit button, edit plus minus, and it's possible to paste here values. So perfect, there is clicked on this cell, and in X cell we must select these 2000 values. Yes, 2000 values, all these 2000 values, copy and paste to this worksheet. Okay, so you can see that we have here values everywhere. So now we will close this window. Yes, we will close this window, and we will delete. Yes. We will separately open these 4 files, these 4 worksheets, yes? So please open it in matrix, for example, for Windows, yes? So please prepare this here like a matrix of 4 Windows. AR3, AR5, AR7 and AR9, yes, matrix of 4 windows with enough space, yes. Okay, so please prepare this. And after you prepare this in eViews, we will check the charts, yes? So please click on the view button, select the graph and line and symbol, okay, yes? And here as well, select the graph, line and symbol, and okay. There is AR3, AR5, click on view button, graph and line and symbol, okay. And also here, view, graph, and again, line and symbol, okay. Okay, so it will be better, yes, to a little bit change the size of these charts. Maybe it will be good to check this chart and this chart, yes. So you can see that there we can observe the differences, yes, small differences, yes. Okay, there is maximum 6, minimum minus 6, there is maximum 4, minimum minus 4, yes. So the range of y-axis is a little bit different. maybe you can see a little bit different development. Yes, if the power of parameter phi is stronger, yes, there is a little bit different development. But better is to check the autocorrelation function. So please open all 4 autocorrelation functions in all charts. Yes. So view button. We must select correlogram of level OK, and open these correlograms in all charts. Yes, view correlogram of level OK, view correlogram of level OK. Perfect. So there is the autoregressive process of the first order with parameter phi equal to 0.3, 0.5, 0.7, 0.9. What can you see here? The typical image, yes, of the development of autocorrelation function and the partial autocorrelation function. In the case of autoregressive process, the development of coefficients of autocorrelation function exponentially decreasing in absolute values. Yes, it's very important that you must imagine all values of coefficients on the right side, even if they are on the left side. Yes, it is valid in absolute values. So you can see, if you check all autocorrelation coefficients, you can see exponential decreasing of values. Yes? So this is the typical for autoregressive process. And the order of autoregressive process is determined by number of significant coefficients of partial autocorrelation function. So you can see the toleration bounds. Yes? In all charts you can see toleration bounds. And here, in the case of partial autocorrelation function, only one coefficient which is higher than the toleration bound is the first one. Yes? The first one. So this is the proof that we have here autoregressive process of the first order. Yes, autoregressive process of the first order. And here you can see exponential decreasing of coefficients of autocorrelation function. Here, yes, if the parameter phi is small, 0.3, you can see that there is not visible, there is not clearly visible exponential decrease of coefficients. Yes, this can occur very often. Yes, if the parameter is small, yes, the size of the parameter is small. You can see autocorrelation coefficient 0.32. Yes, is the size. Yes, there is not significant exponential decreasing. So this situation is difficult in the case that we would like to model this time series. Yes. Okay. So we have here 4 processes, 4 autoregressive processes. Okay, so we are back in this work file as we closed all these processes, and we will try to forecast, yes, some of this process. Yes. And I selected that we will try, for example, the process, autoregressive process with parameter phi equal to 0.7. Yes, so this one, please open this AR07 process. We can check the chart, yes, of this process, view, graph, line and symbol, and okay, so this one. Yes, so it will be necessary to create the model in eView software. Yes, So, in eViews, on the top of this page, click on Quick button, and here we have an estimate equation. So please click on estimate equation, and we will write the formula, yes, of this autoregressive process here in eViews software. So our dependent variable, yes, which is followed by a list of regressors, will be our autoregressive process, so AR space 07, yes, space. And you know that we use only one parameter phi. In eViews software, we will write AR and in parentheses value 1. AR in parentheses value 1, okay. So this is equation specification of autoregressive process of the first order, but many of you at home has different version of eViews. So you must, I have version 8, you have version 11. You must click on options button and you have selected maximum likelihood method for estimation calculation of parameters. So here, Aroma options, you have selected maximum likelihood. You must find here CLS, yes, classical least squares. And in these classical least squares, you will find ordinary least squares, two-stage least squares. So this must be done every time before every your calculation. So remember this. Yes, I don't have to do this because I have old version, but you must do this. Yes, so remember this. Click on OK, and you will see the model. You can see that there is variable AR1, our variable, autoregressive variable, with coefficient 0.68, so almost 0.7, yes, because we set the value of the coefficient 0.7. Okay, so we will try to forecast this time series according to this model. So we can move a little bit this model on the right side, and we must create the space for calculation of predictions or forecast. Yes. So please double click on 500 observations here, and for example, we will add 50 values. So instead of 500, we will write here 550 observation, like end date. Yes. So we'll click on OK, and there is a message that resize involves inserting 50 observations. Yes, I want to continue. Yes. So you can see there is a space now, yes, for the calculation of prediction. Okay, so the model which is behind this chart, the model behind this chart, yes, we must use the model which is behind this chart, this one. Okay, so please click on forecast, and here forecast name will be, for example, AR07F like forecast. Standard error, optional, we will calculate standard errors. Yes? So please write here, for example, SE, yes? SE, E like error, SE like error. And the forecast sample will be from 551 space 550. Yes, 551 space 550. 501, sorry, 501, 550. Okay. I hope that everything else is alright. So we can click on OK, and we will see the forecast. Yes. Okay. So what can you see? This is the forecast. A few observations. Yes, a few observations is possible to forecast, but after the forecast is a conditional mean. In our situation, 0, because this process was stationary time series, yes, and the prediction of stationary time series, yes, you are able to predict only very small number of values, and after you will lose information, yes, you will lose information, and the prediction is the line, yes. So you can train at home if you have eViews or other software. So you can open, for example, autoregressive process with parameter phi equal to 0.9, a stronger parameter phi. You will see that this period will be a little bit longer, yes, but after the prediction will be the line, will be the conditional mean, the conditional average. The mu, the 0 value, because we had originally white noise process with 0 mean. So this is the forecast. Okay, so let's move to autoregressive models of the P order in general. Yes. So, autoregressive model, yes, you already know that we can have more, yes, parameters than one, yes. I showed to you autoregressive model with one parameter phi, where was only one dependence, my value in time t, yes, depends on the previous value, only one previous value, yes, in some measure, yes. But in general, yes, the correlation structure, yes, the measure of dependence can be more complicated, more sophisticated. So in general, autoregressive model of order P can be written like this. X in time t is equal to phi 0, which is a constant, yes? Constant can be placed to the model if it's significant at a particular level of significance, yes? Or this constant is omitted, yes? So the main part of the model is here. So you can see phi 1 xt minus 1, phi 2 xt minus 2, x3 phi 3 xt minus 3, etc. until phi p xt minus p plus a value from the white noise process. Yes? So we have more options, yes? More options to take, yes, to take characteristics, to take dependence from my previous values, yes? So value x in time t can depend, yes, can depend on value in x time t minus 1 and of course t minus 2 and t minus 3, etc., etc. So the structure can be more complicated. So there is written where phi 0 is a constant, phi 1, phi 2, phi 3 are parameters, measures of dependence of locked values, yes, measures of dependence of locked values of your analyzed time series, and AT is white noise with mean mu a equal to 0 and variance sigma squared a, yes. The model is stationary if parameters fulfill some restrictions, otherwise it is non-stationary. So probably we will see these more complicated structures, yes, later. Okay, and now there is exercise plenty. It will not be such complicated, yes. we will use only autoregressive process of the second order. We will generate the realization of stationary autoregressive process of the second order, where AT is a Gaussian white noise with unit variance. There is a formula of our autoregressive process of the second order, and you can see that we have here two parameters phi. So my value in time t depends on my value in time t minus 1, yes, in some measure, yes, and my value in time t minus 1 in some measure, yes, plus a value of white noise, yes. Calculate the sample and true autocorrelation function, so we will check the correlograms, yes, the sample and true partial autocorrelation function, and we will discuss results, yes. And we will try to forecast this time series, this process, which was generated as from white noise process according to this formula. Okay, so we are back in Microsoft Excel, and we will create here autoregressive process of the second order. Yes, we have here in our A column the white noise process, yes, the white noise process, and here in column B, C, D, and E we created 4 autoregressive processes of the first order. Yes, so it will be good to hide these 4 columns, so we can select these 4 columns. We can click on the right button and there is hide. Yeah, so these columns are hidden, and for example here in column F we will write the formula for calculation of autoregressive process of the second order. And if you remember, in our presentation we had written that first parameter phi will be equal to 0.6 plus 0.6, and the second parameter phi2 will be equal to minus 0.4. Okay, so the formula xt is equal to 0.6 times xt minus 1 minus 0.4 times xt minus 2 plus at. So we will start calculate here in the first row, because we don't have first and second previous value, so there is nothing, only the white noise. So there is equal sign white noise on the row where I am placed. Yes, and now I have my first previous value. So in the second row, yes, will be equal sign parameter phi1, which is 0.6. So please write here 0.6 times my previous value. Okay, I don't have my second previous value, so this is omitted, plus the white noise on the row where I'm placed. Yes, okay, enter. So this is the formula on the second row. And formula on the third row. Yes, now I have my 2 previous values. So right here, equal sign, and there is parameter phi1 0.6, yes, 0.6 times my previous value, so value from this cell, yes, minus 0.4 parameter phi2, yes, so 0.4 is parameter phi2 times value from the first row. Yes? So this is x in time t minus 2 plus the value of white noise on the row where I'm placed. Yes? And this, finally, this is the formula of autoregressive process of the second order with two parameters, phi1 and phi2. We can use enter, and this can be copied to the end. Yes, to the end. Okay. And now we will create a space in eViews, and in front of this we will delete the formulas and we will replace the commas for dots. So we must select all values in this column. Yes, all 500 values. We must use copy, Control C. Yes, copy, Control C, and on home leaf, yes, there is paste, the black arrow, and we must paste values, 1, 2, 3, paste values. So the formulas are deleted. And now, again, we must select all these values, yes, 500 values, use shortcut Control H for find and replace. Replace, we must find the commas and replace with dots. Yes, and we'll use the button replace all, and you will see the message that we replaced 500 values, 500 issues. Yes. Okay, so you can see that we have replaced 500 values. And now, in eViews software, in our work file, yes, we must create new file for this autoregressive process of the second order. So we will write here keyword series, space, and we will rename this, for example, AR, like Autoregressive Process 2, yes, space 06 space 04, yes, because we would like to name here the parameters, yes. Okay, so this is the name, equal sign 0, yes, and enter. You will see that we created here another file. We can open this file, and it's necessary to click on edit button, edit plus minus. Please click here on the first cell, yes. And from Excel we can copy these values and paste. Copy Ctrl C and paste Ctrl V here. So it will be good to check the chart, yes, of the development of this process. So click on View, Graph, and use line and symbol, OK. Sorry, there we don't have a values. Yes, we don't have values because in previous example we extrapolated, we calculated the forecast of autoregressive process. So the end, yes, is here. There are no values, zeros, yes, not available values. Okay, so we will try to estimate autocorrelation function and partial autocorrelation function of this process, but it will be better to delete these values. So please click on View button, use Spreadsheet, scroll down and delete the values from observation 501, yes, 501 to the end, delete, yes, and there will be an A not available, yes, perfect, not available values, yes, from 501 to 550. So again, we can click on View button, Graph, and OK, perfect, yes, there is a space for the forecast, but in front of the forecast, we will click on View button, we will find correlogram, so please click in the View button and find the correlogram of level, okay. Wow, this is autoregressive process, yes. So it should be present here exponential decreasing of values of autocorrelation function. So imagine that all values are, for example, on the right or left side, yeah? So on one side. This one is a little bit smaller than expected, but it's alive, yes, it's real life. So you need, yes, a little bit of imagination for see exponential decreasing of the values of autocorrelation coefficients. And in a partial autocorrelation function, you can find two columns statistically significant. Yes? So this is not a typical textbook example, because we had random process, random white noise. Yes? You have a different image, you have a different picture at home. Yes? So you can compare it with me, but I believe that this is auto-regressive process of the second order. Yes? So we will try to create a model, and we will try to forecast this time series. So we can close this. Yes, we can click on quick button, estimate equation, and here we will create the model. So our dependent variable is AR20604, yes, this one, this first one, space, and we will write here AR1 in parenthesis, AR in parenthesis 1, no, AR in parenthesis 1, and after AR in parenthesis 2, yes, AR1, AR2. So this is the formula for autoregressive process of the second order. Yes, and at home, don't forget that you must click on options button, and instead of maximum likelihood, I don't have here maximum likelihood method, yes, but at home you have, so instead of maximum likelihood, here ordinary least squares. So select ordinary least squares, and sample instead of 550, write here 500. Because we have 500 observation. Okay, so there is the model, yes? You can see parameter phi is equal to 0.65, parameter phi 2 minus 0.46. Yes, so it's almost the same like our set parameter in Microsoft Excel. And now, because you can see that we have here 550 observations, so 50 observation without values, we can calculate a forecast. So here on the forecast button, you can see that forecast name will be AR20604 forecast. We will also calculate standard errors. So please write here standard error 2, for example, because we already calculated standard errors. And forecast sample will be 501, from 501 to 550. Okay, so we can click on OK, and you can see that this model is more powerful. There is more information in this model. So if the correlation structure is more complicated, yes, there is more memory inside the data set, yes, and more memory is better for forecasting, because you are able to create a forecast on longer period. Yes, so you can see that there is, for example, the end, and after the prediction is the conditional mean, the conditional average value, the zero, the constant. Okay, again something in general, yes, in general about autoregressive models of order P, yes, how to determine order P of autoregressive models. The true partial autocorrelation function of an autoregressive model of the P order, yes, cuts off at log P. It means is non-zero for logs 1 through P and is 0 for logs greater than P. Yes? Thus, if the sample partial autocorrelation function is non-zero, significant at the 5% significant level, so above the toleration bounds, yes, because in many softwares we have calculated toleration bounds. If the value of the partial autocorrelation function is above this bound, is significant at the 5% significance level. Yes, so if the sample partial autocorrelation function is significant up to log P, an autoregressive model of the P order could be a good choice. Okay, so this is the end. Today we learn autoregressive processes, and next week I will show to you another processes from Box-Jenkins methodology, and concretely it will be moving averages. So I hope that I will see you next week. Have a nice rest of the day, and that's all for today. So bye bye.